Recording. Were you guys able to find your recording from last day? Guys, let me start a little. Hey, box plots. It's going to be kind of confusing for me because like this morning I taught elementary stats, so we're like talking about box plots and how to find the median, and then I go to you guys and you guys are like, so it's a little bit tricky for me to change gears, but especially if this is how I do it. So welcome to the two of you who we haven't met. Nice to meet you. All right, so all right, first thing I'm gonna do, let's see if I can web assign. No. Just want to go to Moodle, show you guys. So what I did was, and you've probably maybe seen it, but what I did was I got on there and kind of cleaned it up a little bit, put some stuff on there. Okay, so just my contact information, right? And so in my office hours, our Zoom ID, right? So all the things that we talked about last day, not in the lab, but and then here you can go and watch the YouTube videos, the grade breakdown, and this is the one that I stole from Claude. And so, but the more I think about this course, I don't know how on earth I'm supposed to keep assignments separate from lab assignments. Because, I mean, so I'm gonna have a really hard time kind of being like, okay, well, here's a concept, but wait until Friday, we'll talk about it. So I do have a suggestion. Does anyone have anything for the next half hour after this class? No.
Another. At 12, yeah.
At 12? Okay. Because what I would suggest is that we just extend this class to be 2 hours on each day, and then not on Fridays. I don't know how you guys would feel about that, but it just means that I could talk about something, show you how to do it, talk about something, show you how to do it. And so I'll check with my boss, but since we're all here, someone's excited. Oh, okay. So, I mean, even if you have a class, it just kind of frees up that little bit of time, right? And also, I think it makes us more efficient in class, right? And just kind of being able to say, hey, here's everything that goes together. And so that makes it even harder for me if I'm able to pull that up. I have to talk to my boss, right? If I can pull that off, right? Then it's really hard for me to say, this is an assignment, this is a lab assignment, right? Because what we should be doing is we should be doing it all together. So I might revisit this because I also feel like 30% of your own work is maybe a bit high for this program. And so I'm gonna go and see what I can do. Right, so that was just what I kind of realized when I took the time this weekend to kind of look at the course and what's going on. I have slated test 1 for February 12th. It is before reading break. It gives you an actual break for reading break. I'm sure you'll have other things to do, right? And from the notes that I stole, I know that Claude had it scheduled so that test 1 is on the regression part, and then test 2 is on the ANOVA part. I'm going to keep that the same way. And so test 2 is on April 1st, so it is kind of right at the very end. But what's nice about doing that is then there's only a little bitty section or a little bitty chapter on logistic regression that you won't have seen on a test before the final exam, right? So that would be the only new thing that you're being tested on. And so that's why I wanted to kind of push it until we could do all of the ANOVA stuff on a test. And then, so it is late, but not too late. Still fine. And then of course, I don't know when the final exam is, but as soon as I know, I'll post it there. But you'll know because the whole campus will be buzzing. The final exam schedule is up. The final exam schedule is up, right? And so, but yeah. So here, the course outline, that was the only thing on here, I think, from Closer. I just left it there. And we jumped right into week 2. So we did introduction, and then in the lab, we did the simple linear regression. I migrated all the lab Moodle stuff to here because I like to just have one Moodle page that I go to, not the 2. And so all the lab stuff and all the lecture stuff will be in the same place. The extra resources you don't really need, right? Here's the lab that you were working on, and here's the notes from last day, even though we didn't write very many notes, right? And so what I did was I've mapped out, this is my wish list for every day, okay? You'll see, and you'll probably be disappointed briefly that I am sticking with the text, but the ebook is $52, okay? And so let's stick with the textbook because I don't know when Claude is coming back. If he's coming back, I don't know. And so that's why I didn't want to change things too drastically and make a real mess for him. And so we'll stick with the textbook, but like I said, the ebook is $52, and so that might be a good option.
Do you know for how long we're going to have access to the ebook?
They sent me, but I get the trial, like the teacher trial version, and I have it for 365 days. So I think it's for the year. I think I was looking, and I think you can buy permanent access, but it would be more, of course. Yeah. I am getting another textbook, so I will put another one on reserve, so there will be 2 on reserve, right? Because, I don't know, the ebook is great, but I mean, it's nice and light. You can have it on your iPad or whatever, but sometimes it's just nice to be able to flip through a hard copy. So once I get my copy, because this one I just stole, so then I'll put that one on reserve as well. And then we can have a couple on reserve. I can maybe lend mine out, maybe. You can also do things that I should not support, right? If you just shared an ebook or whatever, right, that would cut your costs down even more. Share your login. Don't use your usual password type of thing, right? Anyways, you've got options. But yeah, so I apologize, but we are sticking with the textbook, but there are cheaper options. So, so here you can kind of map out, and as we go, I'll add the files, blah, blah, blah. But this is where we're headed. Right? And I've highlighted, well, week 7 is reading break. I still count it as a week because that's a quick win, right? Week 7, done, whew, on week 8, right? And so usually people don't count it as a week, but
February 13th.
yeah, the 17th to the 23rd, or the whole week after the 17th. Yeah. Yeah, so the 17th is family day, and so that's a day off, and then the 18th to whatever is also time off, right? So it's that whole week after family day. Yeah, so you get a week off, but yeah. The labs, besides this first one that we did, I'm gonna have to make it up as I go. There are no labs beyond that point. There might be a multiple regression one, but that's why I've kind of got more regression question mark, but maybe we'll just use that, right? And especially if we're able to condense our class time, then it's not really like a big deal. Then we'll just do R as we go, right? So then it's not really a big deal. Okay, so I will look into combining the lab with the lecture time, right? Extending each day by half an hour. Yeah.
I think there's something else after.
In here,
In here.
yeah. There is a class in here. I've sent off an email. I guess there's a booking freeze, but because there's only 11 of us, including myself, right? We should be able to find a room. So it would be in a different room, but hopefully, yeah. So, oh, thanks for checking.
Yep. And for the ebook, are you gonna post on Moodle the link where we can?
I can do that. Note to myself. I will look into combining. And the only reason they might say no and we would have to do it under the table is because I actually get paid less for the labs. So then they wouldn't want us to combine. Anyways, it's a weird internal thing. So, but then I think we should just do it under the table.
Well, actually, we have this real schedule was on Monday having the labs, but after.
Oh.
Yeah, it was on Monday first.
Wait, it was on Mondays?
Yeah, then Lord changes to Friday because like he don't have time.
Oh, when was it on Mondays?
It was actually from 8 to 10:30, including lab. It's then,
Oh,
yeah.
okay. So you guys are really being jerked around. Here, go here, go here. No, do this. Sorry.
But it was like super early class, that's why he changes his schedule.
Oh,
It's from me.
okay. Yeah, I teach at 8, so we can't do it earlier, but we can extend it after. Nice. So I'll look into combining the lecture and lab. By extending the lecture by, I guess, 25 or let's call it 30 minutes on each day. Goodies. Okay, so I'll look into that. Also note to myself, post link to ebook on Moodle, right? But I think if you just look up Stat2, it's going to be on VitalSource. Have you guys used VitalSource? Hold on. VitalSource before? It's like a ebook bookshelf. So you can have multiple books in VitalSource, and it does cool things, like it lets you make flashcards, it lets you highlight things and make notes on things, and just kind of helps you study. So it's kind of a fun tool. I haven't been able to get it on my iPad app, so I seem to have to open it in the browser. But I was just kind of keyboard warrior this weekend. I need this and I need it now. So I sent off an email to the publisher to see if that was a problem or if that's how it's supposed to be. So anyways, but I'll post the link to the ebook on Moodle, and we'll be working through it, right? Might be nice if, while I still remember, right? Next day we'll go through chapter 2. Chapter 2 is also review, right? From last term, mostly, right? And so we'll do chapter 2 next day. So for next day, read chapter 2. Okay. Was there anything else that I was going to do? I made a note to myself. I think that's it. Okay. Chapter 1. Let's finish that bugger off because you guys have been lingering in chapter 1 for way too long now, I think. And it is all review, right? Regression, you build a model, you're trying to model this relationship. We're talking about linear models in this case, right? And so it is really hard for me to not just start at the beginning, but we'll start and kind of talk about, okay, well, what are some of the assumptions that we have to check? And then what I was thinking was I would show you, because in R, there's a stat2 data package, and it just it has all the data sets that all the examples and all the problems here come from. And even though they only mention it at the very beginning, all the output is from R, right? And so it doesn't show the code, right? So sometimes if it's not obvious, then what I want to do is just kind of show you how they got that output that's in the textbook, right? And kind of make that connection. Okay. So, chapter 1. We talked about, well, we're building a model, right? After we've built a model, right, a linear model, then we want to check the fit of it. And this definitely more review, but just sticking to it, right? And so after fitting our model, we need to assess the fit. And I'll apologize, my writing is not good, but it's not terrible. It gets worse though. So I don't know. But yeah, so I apologize. If there's ever anything that you're wondering about, hey, what does that say? Then don't worry, just ask. And yeah. I'll blame it on writing on the iPad. How about? As a rule. Oh, it's just so hard. It is kind of, but not really. So we need to assess the fit, right? And so how we do that is with the residual plot. And so we use the residuals, right? So the leftovers, we use the residuals to make residual plots to assess the fit. Again, to assess the fit. So what are we looking for? Right. Well, you guys have already kind of talked about it, right? But can stand a refresher. Well, if we plot the residuals against the fitted values, right, that would be the generic residual plot. And so if I've got the residuals against the fitted values, as a rule, if I say y against x, usually I'm looking at, the y-axis, and then I kind of fall it down on the x-axis, right? So the residuals against the fitted values, because sometimes that can be hard to figure out which one goes where. But what we're looking for, so this would be called a residual plot, just in general. Okay. And the residuals, right, the distances from our fitted line to our actual data points, well, the way we fit our line, right, should have minimized the residuals, and so they should be centered on 0, right? And so what we're looking for is this line at 0. Oops. At 0, I'll put that out there, even though that's weird. And we're looking for random scatter, random even scatter around 0. Looking for random even scatter around 0. When you fit a model using the LM command, that model, you can use the model name and $resid. I think it's resid, $resid or residuals. It'll autocomplete it for you, right? And then you've got this column of the residuals. They're hiding, right? You could tack them onto your actual data set if you wanted to, right? But we can access them through that linear model, and I'll show you how, right? Same thing with the fitted values. If you were poking around in the, shoot, what was it called? SS something? SS, plot SS, was that? Yeah. We were playing around with the plot SS, and then we kind of dove into the plot SS code a little bit just to poke around, right? And they had the model $fitted values, and so that's also something that we can access. So when we make that linear model, as long as we name it something, of course, right? We have to grab a hold of it, right? Then we can access the residuals and the fitted values, which means we can also look at, well, do the residuals follow a normal distribution? Because that's the next thing that we want to look at, right? We want to have random even scatter around 0, but if we make a histogram of the residuals, should show, oops, should show a normal distribution. Depending on how large our data set is, right? If we've got a small data set, then yeah, we're more lenient with the shape that we're looking at, right? Because we would argue that it would fill out if we collected more data. If you're looking at 400 data points and it still doesn't look normal, right, then it probably doesn't follow a normal distribution, right? And so we're gonna make a histogram of these residuals and make sure that it follows a normal distribution. The residuals following a normal distribution, we can check a couple of different ways, right? We can make a histogram, and I think that's the easiest thing to do, right? Just kind of look at it. Does it look like a normal distribution? Could we argue that it would be a normal distribution, right? You can also make, have you guys talked about QQ plots? Quantile plots, sort of. Right, that's when we plot the observed against the expected, I think. Is it the other way around? Anyways, and so if the observed is the same as what we're expecting, if they followed a normal distribution, they should follow this diagonal line, right? And so, or a QQ plot should show a straight diagonal line. To indicate a normal distribution. In my lower classes, I'll often capitalize the normal And so sometimes I flip between capital N and lowercase n, just to emphasize that it's just the name. So sometimes I'll write capital N, lowercase n. You guys are flexible. So you know that it's a shape. We've got other options, right, for checking normality, right? Oh, sounds important. Yeah, right, we want to have this normal distribution of the residuals. We can even do a hypothesis test, the Shapiro-Wilks test. The textbook doesn't talk about it, so it's not going to come up on a test or anything. And as a rule, test material will be confined to in here. Hey, it looks manageable. That's all you have to learn. Not bad. I like small textbooks like this. But anyways, so material will be from here, right? I'm not going to expect you to go beyond, right? I might expect you to apply it, right, in a kind of a chain link way, right? Well, this is this because of this, but all the concepts will be from here. Right? So I'm not out to get you guys. Should feel reasonable at least. Right? Or, and this is not in the textbook, but I think it's important to know that it exists, right? We can do a hypothesis test, right? Does this follow a normal distribution? The null hypothesis is, yes, it's a normal distribution, right? The alternative hypothesis is, no, this does not follow a normal distribution. That's not what we want, actually. So this is one of those scenarios where we don't want to reject H naught, right? So we want a high p-value, right? And so we can test for normality using the Shapiro, oh, this is a name, so I should capitalize it. And I think it's Shapiro dash, I'm not even sure if it's Wilk or Wilks. We'll do that. You guys can probably find out pretty quick. Shapiro-Wilks test, right, where H naught is
Yeah, Shapiro.
without the S. Thank you. Thank you. The H naught is that the data follows a normal distribution. Right. Usually I don't even give the alternative hypothesis unless I'm asked to, because it's just the opposite of the null hypothesis, right? Either follows the normal distribution or it doesn't. Right? So there's lots of options for checking if the residuals follow a normal distribution. Right? We're also looking for things like constant variance, right? And we can get that from our residual plot, right? If it doesn't have random scatter around 0, right? There could be things like nonlinearity, right? If there's kind of a scoop in the shape, right? So it's not random, it seems to follow some sort of pattern, right? Then we probably shouldn't have fit a straight line to it. Right? And so what you'll see is the residual plots show you basically the same thing that the scatter plot with the line on it does, except it magnifies that relationship, right? So it magnifies, well, how are these dots behaving around the line, right? But they'll look very similar, right? If there's a curvature in your scatter plot of your actual data, then there's going to be a curve in your residual plot, right? But it's going to be even more noticeable. Okay. So the residual plot,
What do you do after establishing null hypothesis and alternate hypothesis?
then you do it in R. Yeah.
You have,
I think there's a Shapiro.wilk.
you have command, function for Shapiro.
Oh yeah, Yeah.
You can do that.
Yeah.
Directly in the plot.
and heck,
Yeah.
why not? Let's look at it in a little bit here to satisfy that.
You have an argument called method. You can choose Pearson or Shapiro.
Oh, yeah, I was poking around and yeah, I guess there is just the Shapiro.wilk command. So,
Yes, package.
Stat
probably.
2, I guess. For stat 2, we use covariance, cover, COVR, or all the other statistical and all these non-parametric tests and all, with stat 2 package.
Nice. And I wonder if that's, yeah, is that related to this one?
Which one?
Probably. The stat2 package, because we use the stat2 data. I wonder if they're related.
I'm not sure if stat 2 package is related to this textbook, but
We'll-
I know stat 2
We'll
package.
poke around. We'll poke around in there. Okay. Oh yeah, so the residual plot will always look similar to the scatter plot of the actual data. To the scatter plot of the actual data. Right. But deviances from the linear model will be magnified. But I guess I'll say deviations, oops. But deviations from the linear model will be magnified. Right. Just like that. So, things that we would see, right? The most common things to look out for if you're looking at the residual versus the fitted, right? Here's our line at 0. If we've got something like this, right? Well, this is probably nonlinear and we shouldn't have fit a straight line to it, right? Because it would have looked the same when we decided to fit the straight line to it, right? And so this would be nonlinear, right? Which means the linearity assumption was violated, right? That's saying the same thing, but I'll put it on here. Right, so the linearity of assumption was violated. Another thing to look out for, again, if you've got this residual against the fitted values around 0, if you've got something that looks like this, too much papa papa, right? Here, we have non-constant variance, which is the same as saying, well, the constant variance assumption was violated, right? And so here, we summarize it as saying we have non-constant variance. Which is just saying that the constant variance assumption constant variance assumption was violated. Okay. So those are just two assumptions, right? Usually we can detect these by just looking at the scatter plot, because your scatter plot, well, it would look the same, right? Except usually your line, let's say you have a positive relationship, it would just look like this, right? The problem with constant variance, I think we all understand. If we're fitting a straight line and we don't have a straight line in our data, that's a problem, right? The problem with constant variance is that, yeah, there is no other choice than a straight line here, right? But the problem is that for these values of x, right, our model is doing a really good job, right? Things are nice and close, things are happening here, and our predictions, right, are going to be really good. But then, how do we communicate to someone reading the model that, well, after this point, it actually doesn't do a very good job, right? And so that's the problem with the constant variance, right? Is that, okay, well, here it's great, here is not so good, right? If we had just looked at this cloud, it doesn't necessarily, like, we could put the line anywhere, right? And so if we've got non-constant variance, then we need to do something about that. And we can deal with that by doing a transformation, right?
This is all once we come up with a with a model, right?
Yeah. Mm-hmm.
Be it
So-
be exponential or logarithm.
For right now, we're only talking linear models, but yeah, in general.
Yeah,
In general.
Fitted values are those where we have already done something.
So we've already fit a model, right? And usually how it works is you've got mod 1, mod 2, mod 3, mod 4, mod 5, and you just keep running these models, copy and paste your code, and just check the residuals to see which one is going to be the best one, right? You tweak things later on, right? We'll add variables, we'll take away variables, we'll take away outliers, we'll add them back in, see what's happening, right? And so usually we've just got this huge long list of little tweaks on our model, trying to figure out which one is going to work the best, right? For things like this, right, non-constant variance, one nice option for the transformation is the square root. If you think about how a square root behaves, right, the square root of, let's say, a small residual, right, a small number, the square root of that, it's not going to change that much, right? So these small residuals, they just stay small. They don't, they don't change that much when you take the square root. However, a large residual, right, if you take the square root of it, then we kind of get it to clam up, right? Doing the opposite of squaring values, right? So in the transformation here, if the constant variance assumption is violated, right, one of the first transformations that we can try is the square root, for example. Okay. And so, oops. If the constant variance assumption is violated, the first transformation that we can try might be the square root. The first transformation try might be the square root. And then you can kind of think back, okay, well, how does the square root behave, right? It's not going to affect those small residuals, but it's going to tighten up those large residuals around the line, right? And
But
so,
if you do a square root for those large ones, even these won't these go under that?
so the key is, so when we do a transformation, what we do is usually we transform the response variable, or at least for me, I transform the response variable, so the y, right? And so then I need to remember that, okay, well, my model is actually modeling the square root, right? And so to undo that square root, the result, if I'm predicting a value, for example, I'll need to square it, right? So I always need to undo the transformation after, which can make interpretation a little bit tricky, right? Because if we've done a transformation, then we have to undo it when we're interpreting the values. Okay? So let's write that down. If we do a transformation, our model, and usually I'll say predictions because usually that's why we're modeling things. We want to predict future values or unknown values, right? So we want to make predictions, right? And so if we do a transformation, our model is predicting the transformed value, right? Our model is predicting the transformed value. Okay. This means that in order to interpret it, right, we need to untransform, right, or reverse the transformation. I prefer untransform, even though I'm not sure it's a word, but. And so, therefore, in order to interpret a prediction, we need to untransform the predicted value. Right. So we started talking about the square root because I think it just makes more sense, right? We can think about how the square root works, and then we can kind of convince ourselves that, yeah, those residuals would tighten up around the line. If we go back to our nonlinear, so the linearity assumption is being violated, right? That means we shouldn't have fit a straight line to begin with, right? So even maybe before we even fit the line, what we can do is we can do a log transformation, right? So usually to fix a nonlinear data set, right, we can do a log transformation, and usually that'll kind of straighten things out. Remembering that now we're predicting the log values of the response and possibly using the log values of the explanatory variable as well. So you're allowed to do the predictor as well as the response, right? So you're allowed to do your X and your Y if you have to, right? I usually start by transforming my Y, right? See what happens. If it's still not quite linear, then I transform my X, right? My explanatory or predictor, if you want to call it that. And then hopefully it'll be linear, right? So I usually do it kind of step by step, right? Check the Y, okay, I still need to do a little bit more work here, then I transform the X, right? And so give it some time.
So untransform as in square root and the
Yeah.
squaring again.
So
Squaring to different variable.
so let's say, okay, here, now that it's all caught up, why is it being so slow? Come on. Right, and so if you've got something like y hat is, are you guys using, I can't remember,
B naught.
B naught, B's? Okay, so B naught plus B1x, you can really use any A, B, B1, B2, but that's weird. Right, so here, this would be your model if you just had a straight, so this is untransformed, right? If you transform your y's, right, then let's say your square root of y, oops, would be your predicted value, right? The hat just says predicted value of the square root of y. And if we've got, you know, B1 or B naught plus B1x, right, this is the transformed value. If we have some value of x that we're predicting at, right, then let's say the predicted value of y, the square root of y, turns out to be 4, just to keep it nice and simple, right? Then if you have to find the predicted value of y, right, we would square both sides. And so it just depends on the transformation that you did, right? You have to undo it just to solve for essentially y hat. Right? And so if you take y hat is, 4 squared, so then y hat must be 16. Does that make sense?
Yeah.
So that's what I mean by untransformed. This is the untransformed predicted value of y. Okay.
It goes into the x as well, right?
Yeah, if you've transformed the x, then yeah.
Yeah, if you're transforming X,
Mm-hmm.
because which
Then-
you won't be doing it because that's independent of the system.
You can do it.
Oh,
It depends on your data and your fit, how much you want to fit.
why would we change the independent? Because we generally tweak dependent.
Sometimes you might find that you have to change the independent as well.
Okay.
Right? But then up here, instead of, let's say you applied a square root transformation to the x as well, then the y hat, the square root of y hat would be with the square root of x in here. But usually what we do if we just put in the square root of x as our x, right, or as our explanatory, we're still just going to get a number, right? And so we've taken that into account when we found that value. And so for nonlinear data, right, if we find our data is nonlinear, the first transformation to try is the log transformation. The first transformation to try is a log transformation. in stats and most other fields, right? When we say log, we mean log base E, which is ln, right? And so when I say log, you say how high? No. Right, so if I say log, really what I mean is log base E, which is ln, or usually if I'm writing it, because we usually end up writing it a lot, I just do a cursive ln, just so you can recognize it if you see, oh, there's some weird thing going on in here. So I mean log base E, but to make it extra confusing, when I say log, right, I mean log base E, or the natural log, and so ln. Forget log base 10, we'll probably never deal with. So log base 10 is for frequencies, so like sound and that kind of thing. And so that's not really, I don't know, doesn't really come up for us. So for us, we need the natural log. And so if I write ln, I'll read it out as log, and I know that's really confusing, but you'll get into the groove of it, right? And so,
How they affect in transforming the data? What is the magnitude? How they change log base 10 and log ln?
so the logs, right, is a little bit trickier because we have to think about the graph of a log, right? And so the graph of a log, right, typically just kind of looks like, right? And so for small values of x, right, we're going to get negative values, and then past 1, right, it always passes through 0, 1, or sorry, 1, 0. But the reason I started with the square root, even though we talked about the linearity assumption because it's the most obvious, is because the log transformation is less kind of, we can't really grasp it, right? For me, there's no way that I can think, oh, well, that's obvious because this is how the log behaves, right? And so, yeah, I kind of have a hard time with that. And so just as a rule, right, the log transformation usually will help you straighten things out, right? And so that's what I want you to remember, right? Because the square root is fine. We can think about how the numbers behave and kind of convince ourselves. Here, we don't really think in logs, right? And so the log transformation, right? Usually I start with the response variable, and then if needed, I can transform the explanatory variable as well. So I usually start by transforming the response variable. I usually start by transforming the response variable. If the relationship is still not quite linear, if the relationship is still not quite linear, we can also transform the explanatory variable. We can also transform the explanatory variable. Yes.
So if you transform the y with, say, log,
Mm-hmm.
can you transform x with, say, square root?
Yeah, sure.
Yeah.
Yeah, you can mix and match.
Or
It's going to be very hard. It might be very hard to undo your transformation though,
Yeah, but
Because-
for this,
Mhm.
so if you transform that, then we transform that as well. or-
Yeah. Yeah, so usually I would apply the same transformation. There's no rule that says, no, you can't do that. But if you think about, okay, so if I've got the log of y, right, and that's my predicted value, is b naught plus b1 square root of x, right? Now, if I had to apply and solve for y hat, right, I would take e to the power of both sides, and then I'd have e to the power, and then I'd have a square root in there. Not a problem if you have the value of x, but if you're solving for it algebraically, it can get a little bit messy. And so that's the only reason that I would kind of, preferably not, right? But that's only if I have to solve it by hand. If I already have a value for the log of y hat, who cares, right? Then you can do whatever you want to the x, right? And so does make it a little bit trickier if you have to solve for it by hand, right? And so here, whereas if I didn't have the square root of x, but I had the log of x, right? If I took e to the power of this and then all of this, right, it's going to be easier to solve for. So then I can break it up, e to the b naught and then e to the b1 ln, which I could rearrange and just kind of solve for easier.
And in what cases we also try to change x or transform x?
If you've transformed the response, right, if you've transformed y and it's still looking kind of nonlinear, then, I mean, have a look at the residuals. Maybe it's not that bad, probably is. So then you would go, okay, well, now I'm going to transform both of them to see what happens. You could even play around with it, right, and say, well, what if I don't transform y and instead I only transform x, right? That could be an option, right? And so, yeah, it turns out to be just a ton of just copying out your code. Copy, change one thing, run it. Copy the code, change another thing, run it. Always commenting your code.
Yeah.
Oh, this will be so obvious to me later. No, it never is. Right? And so, I'll remember. How could I forget this moment? No, you do. So definitely just make a note, like changing this, changing that, whatever. But you're not reinventing the wheel. Once you've built a model, you're just tweaking it, changing one or two things to see what happens. And then how you assess it would be your residual plots, right? How good do your residual plots look? Do the residuals look normal? Is there random scatter around 0 if you plot your residuals against your fitted values? That kind of thing. Right? And so I always found it really overwhelming when someone said, oh, you just do a transformation. You're like, but how am I supposed to know what I'm supposed to do here, right? And so just to start out, right, let's have it as a hard and steady rule that if you've got non-constant variance, try a square root, right? See what happens, right? Maybe to one, maybe to both, right, x and y. If you've got non-linear data, right, try a log transformation, maybe on one, maybe on both, right? And so let's just kind of boil it down to something that simple. And then as we go, right, I think you'll feel the need to kind of tweak that a little bit, right? Oh, what if I change it to, I don't know, I can't even think of something that might work, right? Because usually those ones do the job. Okay, so that's transformations. Let me see here. Oh man, time flies when you're having fun, hey? Yikes. Okay, when do we go till? We go till 10 till 11, right?
Yes.
Okay, so I guess let's just do theory today. And then bring your laptops next day, and then we can run through it and I'll show you how to do it in R. And what I want to do is then you'll have had a peek at the textbook, and we'll just go through those examples so that we can kind of make the connection between the examples in the textbook and what we're doing here, and how to do it in R. We also need to finish just talking about outliers. Okay. Outliers are extreme data points. We usually talk about two different kinds of outliers, right? So there's just these extreme values that follow the same trend as your other data, right? But then there's values that are, you know, in the vertical direction different from your data, right? And so we can talk about two different types of outliers. So if we've got our X and our Y, and most of our data is just kind of hanging out here, right? And then we've got one data point down here, right? Even if it's one or two, right? This doesn't really, it might not influence the line, right? Our line of best fit. Remember, our line of best fit is trying to minimize the residuals to all of these points, right? So it's going to try to capture these far points. But notice that even visually, if you have a look and you try to fit a line just to this data, right? It might look something like this, and yeah, sure, it looks like this line will be captured, right? But it's possible, because it's got this kind of leverage, right? If it's moved up a little bit, then it's possible that the line is trying to make up for that, right? And so I'm 90% sure, because I use the term leverage, that this would be a leveraged outlier, and then the other one is influential. I'm gonna cheat. Well, it's not really cheating. I've just been blah, blah, blahing this whole time, so I think that's pretty good. Where was it? They're just saying, hey, these are residual plots. Anyways, until further notice, let's call it a leveraged outlier. I can't find it. Did read about it though, so it's in there. And that's when it's like out here, right? And away from the.
Yeah.
I wish I could Command F in here. Search. Yeah, I'm pretty sure. Anyways. And let's just draw out the other one that we were talking about, just so we have them both. I reserve the right to change the name, but I'm also feeling pretty confident. Won't that backfire if I'm wrong? No, I'm pretty sure. So again, right now we've got most of our data kind of hanging out. Usually I draw a positive relationship, I'm not sure. Glass half full. So then here, this point would be considered influential, right? So it just depends on where it is in relation to the data, right? If it's just kind of following everything else, right? Then usually that feels like it's a little bit better, right? But regardless of what type of outlier we have, what we're gonna do to deal with these things is usually we fit the model with all the data points, right, regardless. Then we fit the model so that you copy your code and then you make a subset of your data set where you removed the outlier, right? And then you check the fit of that model. Right? And usually it ends up being kind of a judgment call. Like usually we want to keep all our data sets. Right? And so if I can argue that, well, my model didn't change very much when I removed this outlier, so I'm just going to keep it in there just so I can keep all my data, right? And so we look at the model fit and compare the model fits with the outliers, without the outliers. If there's more than one outlier, right? Let's say we have another one up here, we would remove them slowly, right? One by one, so fit with all the data, remove the first one, put it back in, remove the second one, put it back in, model it with both of them removed, right? And so we play around with all the different combinations. And so if we have outliers, we fit the model with all the data. Then remove the data, or remove the outlier. Then don't remove the data. Then remove the outlier. I'll put in brackets outliers incrementally, right? Taking them out, putting them back in, right? You don't make big changes, right? You make little tiny changes. Outliers incrementally. So then remove the outlier and assess the fit of the new model.
When you say incremental, say one by one, can you do it in clusters?
Depends on how many you're dealing with, I would say. If there's a lot that are similar in a cluster and you have like 5 of them, right? It's more of an art, right? You kind of say, oh, I'm going to remove 1 of these, I'm going to remove 2 of these, I'm going to remove all of these, right? And so you just kind of make those tweaks, tweak. And so, yeah, we don't like that when there's no rules, right? It's just going to be kind of, it depends on the data, I guess is the answer. Yeah. Mm-hmm. Because if things are in a cluster, then probably removing 1, 2, or 15 of them, right? They're all going to have about the same effect. So, yeah, it just depends. Yeah.
In general, you have the formula for outlier, Q1 minus 1.5 Q1, but it's a single data point.
Yeah. So here we've already established that they're outliers, right? And so we can use that using the 1.5 IQR rule. Right? But now we need to know what to do with them, right? And so how they affect our model, right? So we have established that they're outliers. Something extreme like that, or like especially this one, right? We probably wouldn't need the 1.5 IQR rule to say, yeah, that's probably an outlier, right? But you could make a box plot of the data just to make sure, right? And it'll give you the outliers. Good. So, yeah.
My question was, the formula was only for if you have a data set like 1, 2, 3. But if you have an ordered pair, the formula doesn't work.
Right, so then you could focus on the X or the Y axis. Yeah. Yeah, and I guess it kind of depends on what type it is. All right, like here you would probably look at I would look at the X axis, whereas here I might look at the Y axis. Right, just depends. But yeah, thank you. Like, what? What's the problem? No, now you got X's and Y's. All right. Any questions? No? So next day, bring your laptops. We'll poke around with this stuff, right? Get into the textbook, skim through chapter 2, and then we'll be able to kind of breeze through it a little bit better, because I always go slower than I want to. I guess it's good, but anyways, see you guys on Wednesday.
See you.
Thank you. Oh, I didn't even realize you made your own.
Yeah, that's
Nice.
what I'm saying, like, we have this thing. We
Uh-huh.
want to market it.
Oh, so I'm not the first, you mean? That's good.